Section: Introduction. In this section, we delve into the recent progress made in large language models, LLMs, and their remarkable ability to handle a variety of tasks, including answering complex questions that require multiple steps of reasoning. These models are now also capable of processing longer pieces of text. This advancement prompts us to investigate how well these models perform when dealing with these longer inputs, which they are technically equipped to handle. We ponder whether the ability to support long inputs translates effectively across different tasks, allowing a model that performs well with short prompts to maintain its performance with longer ones. Recent research that tests these models with tasks involving longer texts, especially those requiring reasoning, suggests that models often find it challenging to process long inputs. However, these studies might not be entirely reliable as they change both the length of the input and the task simultaneously, making it difficult to determine if the performance drop is due to the longer input or the complexity of the tasks. In our work, we aim to isolate the impact of input length on model performance by keeping other variables as constant as possible. We introduce a method to track how model performance changes with input length by focusing solely on this factor while keeping the task the same. To achieve this, we present the Flexible Length Question Answering Dataset, FLENQA, a dataset designed for text-based reasoning. This dataset includes true-false questions that require understanding two pieces of information, the context, to answer. We create multiple versions of each question with varying lengths by embedding the necessary context within longer, irrelevant texts. This design ensures that models must use the entire input to answer correctly, as both pieces of information are essential for the correct answer. Yet, we ensure the tasks are simple enough that models can easily answer the questions when the information is presented without additional text. Our findings reveal that LLMs experience a significant drop in reasoning capabilities with inputs as short as 3,000 tokens, which is well below their maximum capacity. On average, accuracy falls from 92% to 68% across all models tested. We also explore how the placement of relevant information within the text and the similarity of the context to the information affect performance. Our results show a consistent trend of performance degradation, regardless of these factors. Moreover, we discover that a model's ability to predict the next word in long inputs does not correlate with its performance on reasoning tasks with long inputs. Additionally, while using a chain of thought, COT, prompting method improves performance on short inputs, it does not significantly counteract the performance decline seen with longer inputs in most models. The exception is GPT-4, where the gap between COT and standard prompting widens with longer inputs. Finally, we analyze our results to identify common failure modes in model responses. We find that with longer inputs, models often ignore specific instructions, either providing no answer or, in the case of COT prompting, presenting the final answer without the reasoning steps. There's also a noticeable bias towards false answers and a decline in the model's ability to incorporate relevant information as the input length increases. Our goal is to understand how the length of the input affects LLM's reasoning capabilities over text, assuming the relevant information remains unchanged. We focus on question-answering tasks that require models to reason over given texts. To ensure our findings are applicable to both open and closed models, we adopt a behavioral approach that relies on manipulating the input. We emphasize that the task must be solvable only by drawing conclusions from the text, requiring all relevant text spans to be considered together for a correct solution. We avoid tasks that can be solved by breaking them down into smaller parts, as these do not truly test reasoning over long inputs. Additionally, we ensure the questions and relevant text spans are based on novel facts not seen during training to prevent models from relying on pre-existing knowledge and to avoid data contamination. We also make sure that the reasoning required is independent of the input's length, the added text does not interfere with the reasoning process, and the placement of relevant information within the input is controlled. Section Summary. In this section, we investigate the impact of input length on large language models, LLMs, when reasoning over text. We introduce the Flexible Length Question Answering Dataset, FLENQA, to study how LLMs perform on tasks requiring reasoning over longer inputs. Our findings reveal that LLMs experience a significant drop in reasoning capabilities as input length increases, even on inputs shorter than their technical maximum, highlighting challenges in maintaining performance on longer inputs across various experimental settings. Section: Maintaining natural-looking inputs. In this section, we focus on ensuring that the inputs look natural, as if they were something a user might actually type into a language model. For instance, a bunch of random sentences thrown together doesn't seem natural. However, if we have unrelated paragraphs that are each internally cohesive, this feels more natural because it's similar to gathering information from various sources. To keep inputs looking natural, especially when we're playing around with their length, we make sure that at least each paragraph makes sense on its own. We're excited to introduce the Flexible Length Question Answering Dataset, or FLENQA for short, which meets the criteria we've discussed. FLENQA includes 3 reasoning tasks: monotone relations and people in rooms, both of which are new, and a simplified version of RuleTaker. Each task starts with 100 base instances. From these, we create variations by changing the length, adding different background texts, and spreading out the facts differently within those texts. We've made sure each task has an even number of true and false answers, and that language models can solve most of the base instances correctly without any modifications. We're releasing this dataset to help further research into reasoning and how well models handle long inputs. You can find more details and statistics about these tasks in the appendix. Let's talk about what goes into each base instance. There's an optional prefix, which might introduce the task or provide some supporting facts. Then, there are 2 key paragraphs. Each one is focused on a theme and starts with a crucial sentence that's needed to solve the task. Sometimes, there's an optional suffix, like a question that refers back to the context provided earlier. When we put these instances together for the language model, we separate the different parts with new lines. In the text, we highlight key paragraphs in red, with the most important sentences in a darker shade of red, and any optional parts in black. The full prompts for each dataset are available in the appendix. When creating the key paragraphs, we start with 2 facts, each expressed in a simple sentence. We then use GPT-4 to expand these sentences into paragraphs that stick to the theme without adding new information. Afterward, we manually check to make sure everything looks good. Now, let's dive into the tasks themselves. For monotone relations, each key sentence compares 2 people on a scale, like X is taller than Y, or Y is older than Z. Then, we ask a true-false question about a relationship between 2 entities that weren't directly compared in the text. These relationships are transitive and follow a consistent direction. This task is inspired by how we describe kinship in various cultures, and we've come up with a new set of relationships for this work. We create the data by randomly picking names and relationships, ensuring a variety of scenarios. In the People in Rooms task, 1 key sentence places a person in a specific room, like X is in the old library, and the other describes a feature of that room, such as, the old library has wooden floors. The challenge is to figure out if the person is in a room with the stated feature. This dataset draws inspiration from the Bobby tasks, focusing on the movements of agents, but we've simplified it to involve just 1 agent. We carefully choose names, rooms, and properties to avoid any confusion. Lastly, the simplified RuleTaker task is based on RuleTaker, a benchmark for proving theorems within texts that lay out logical theories in plain language. Each instance includes a logical rule, 2 sentences that introduce facts, and a question that asks about the relationship between the rule and the facts. By tackling these tasks, we aim to push the boundaries of what language models can understand and reason about, especially when dealing with complex or lengthy inputs. Section Summary. The Flexible Length Question Answering Dataset, FLENQA, introduces 3 reasoning tasks: monotone relations, people in rooms, and a simplified version of RuleTaker, each comprising 100 base instances with variations in length, background texts, and fact dispersion. Key paragraphs in FLENQA are created by expanding simple sentences into thematically coherent paragraphs using GPT-4, ensuring natural inputs for LLMs. Monotone relations task involves comparing person names on a monotone scale. People in rooms task infers a person's location based on room properties, and simplified rule taker task focuses on theorem proving with logical rules and facts. Section: Length variations. In this section, we discuss how we adjusted the length of each base instance to have input lengths of approximately 250, 500, 1000, 2000, and 3000 tokens. To achieve these lengths, we added extra text that doesn't relate to the main question, which we refer to as padding. For every combination of a base instance and a target length, we created variations by changing the source of the padding text. This padding could be identical to, similar to, or completely different from the key paragraphs of the instance. Additionally, we experimented with how dispersed the key paragraphs were within the padding text. For the duplicate scenario, we wanted to see what happens when the input length increases but the information stays the same. Here, we simply repeated the key paragraphs to reach our desired input length. This setup made one part of the question answering task, identifying the key information, very straightforward. In the similar scenario, we used paragraphs from other base instances of the same task as padding, making sure not to include any paragraphs that could contradict the key paragraphs. This way, we avoided creating any misleading or confusing versions of the instances. For the different scenario, we turned to the books corpus for padding text that was unrelated to the key paragraphs. We carefully inserted the key paragraphs into randomly selected text from the books corpus, ensuring they fit naturally within the sentence boundaries. We also explored 4 different ways of placing the key paragraphs within the padding text. They could be placed at the beginning, in the middle, at the end, or randomly throughout the text. Each placement strategy had its own implications for how the key paragraphs were encountered during the reasoning process. We checked the baseline accuracy of language models on these base instances by evaluating them on the minimal text needed for answering the questions, which included just the question and the relevant key paragraphs. Surprisingly, even without complex prompting strategies, most models performed quite well, indicating that they could find and use the key information effectively. In our main experiments, we reported average accuracies across all tasks and kept the experimental conditions consistent across different input lengths. We tested 5 recent large language models to see how they handled the tasks. We specifically looked into how the length of the input and the placement of key paragraphs affected the model's ability to reason. Initially, we examined what happens when only relevant information is added. This scenario showed that adding irrelevant text significantly reduced the model's performance, as they no longer needed to search through the input to find the key paragraphs. This finding was unexpected because it suggested that the length of the input could still influence performance, even when the models didn't have to identify the relevant information from a larger pool of text. Moving to a more realistic setup, we included both key and irrelevant paragraphs in the prompts. We found that the model's ability to correctly answer questions was influenced by where the key paragraphs were located within the text. Placing the key paragraphs together in one spot meant the models only had to focus on a single area, which generally led to better performance. Our results showed a noticeable decline in accuracy when the input length exceeded 500 tokens, but interestingly, placing the key paragraphs at the end often resulted in the highest accuracy, hinting at a possible recency bias in the models. Section Summary. In this section, we explore the impact of varying input lengths on language model reasoning performance by extending base instances to different token lengths. We create different versions of each instance with background text that is either duplicate, similar, or different from the key paragraphs, and vary the dispersion of the key paragraphs within the background text. Our experiments reveal that even in scenarios where only relevant tokens are added, accuracy decreases with length for all models, and the position of the key paragraphs in the text influences model performance, with adjacency often resulting in higher accuracy. Section: Non-adjacent relevant paragraphs. In this section, we delve into the scenario where the necessary information is scattered across two non-adjacent parts of the text. Our findings, illustrated in a figure, reveal a significant decline in performance as the text lengthens. This suggests that the task of reasoning becomes considerably more challenging for large language models, LLMs, when they are required to gather evidence from two separate sections within a longer context. Moving on, we concentrate specifically on cases involving non-adjacent key paragraphs and examine the impact of irrelevant text. We explore two different situations, one where the irrelevant paragraphs are similar to the relevant ones because they come from the same task, and another where they are different, originating from a book's corpus. Initially, we assumed that models would find it easier to ignore paragraphs that are different from the relevant ones, thereby making it easier to focus on the necessary information. Contrary to our expectations, the results indicate that the performance drop is generally larger when the irrelevant paragraphs are different, not easier as we had anticipated. We also investigate the relationship between perplexity and reasoning accuracy. Perplexity is often used to gauge how well models can predict the entirety of their input. However, it's been shown that a model's performance on downstream tasks doesn't always align with its perplexity. Since we can't measure model perplexity directly due to the closed nature of the models and their full vocabulary token probabilities, we measure the accuracy of predicting the next word in a given text. If the model's prediction matches the actual next word, it's considered correct. Our analysis, using our dataset but excluding the questions, reveals that while next word prediction accuracy tends to increase with longer inputs, it negatively correlates with reasoning performance on these tasks. This suggests that next word prediction accuracy, and by extension perplexity, may not be reliable indicators of a model's reasoning capabilities on longer texts. Regarding the chain of thought, COT prompting technique, which encourages LLMs to outline their reasoning steps before arriving at an answer, we experimented to see if it could improve performance on longer inputs. The technique has been shown to enhance accuracy on various reasoning-based question-answering tasks. However, our experiments reveal that its effectiveness varies across different LLMs and generally does not counteract the performance decline associated with longer inputs. While COT prompting does improve performance in most cases, such as with GPT-4 and other models, it only significantly benefits GPT-4 as the input length increases, making it a somewhat limited strategy for mitigating length-related performance issues. Interestingly, for the Gemini Pro model, COT prompting actually worsens performance as input length grows, despite boosting performance on shorter inputs. Lastly, we identify 4 patterns of failure that correlate with incorrect responses in our results. These include a refusal to answer with a clear, true, or false, as instructed, which becomes more common with longer inputs, a bias towards one of the labels, typically false, as input length increases, a tendency to provide the final answer before the expected reasoning steps when using COT prompting, which goes against the intended use of the technique and does not improve performance, and a statistical link between incorrect responses and the occurrence of answers before reasoning steps, highlighting a failure to adhere to prompt instructions as the length of the input increases. Section Summary. In this section, we investigate the challenges faced by large language models, LLMs, when collecting evidence from two non-adjacent locations within a text. Surprisingly, we observe a significant drop in performance as the length of the context increases, making reasoning tasks notably harder for LLMs. Additionally, we explore the impact of irrelevant text on model performance, finding that having irrelevant paragraphs different from the relevant ones does not necessarily aid the model in focusing on the key information, as initially expected. Section. Chain of thought lack of coverage. In this section, we discuss the challenges that arise when large language models, LLMs, are tasked with processing and reasoning over long inputs, specifically within the context of the Flenka dataset. We've observed that these models struggle to identify and focus on relevant pieces of text as the length of the input increases. Ideally, we would want the models to pinpoint the important texts and include them in their reasoning steps, but unfortunately, their ability to do so diminishes with longer inputs. This was demonstrated by our analysis, which showed a decrease in the coverage of key sentences in the model's outputs as the input length grew. We also noticed that the model's incorrect responses were often linked to their failure to fully cover the necessary facts. In our review of related work, we found that the evaluation of LLMs on long inputs has primarily followed two paths: benchmarks of downstream tasks and next word prediction tasks. While benchmarks with long input samples offer a direct way to assess model performance, they limit our understanding to fixed input lengths and do not fully explore the impact of varying lengths. On the other hand, next word prediction tasks provide some insight into how models manage different input lengths, but their correlation with overall performance has been inconsistent. Our study builds on this existing research, focusing on the specific impact of input length on model performance. Through our investigation, we've discovered a significant decline in reasoning performance with longer inputs, occurring even before the models reach their maximum input capacity. This was evident in our experiments with the Flenka dataset, which was designed to isolate the length factor by adjusting irrelevant parts of the input. Our findings highlight a clear negative impact of input length on reasoning performance, regardless of adjustments made to the input samples. We also identified specific areas where models failed, such as in following extended instructions and showing biases towards less relevant information. These insights provide valuable directions for future research to improve LLMs. In conclusion, our work suggests that evaluating a model's performance based on a single input length does not offer a complete understanding of its capabilities. A more nuanced evaluation is necessary to truly gauge a model's performance across different lengths. We argue that for a model to be considered effective at processing long inputs, it must maintain consistent performance across all supported input lengths. However, our study does have limitations. The observed performance drop with varying input lengths remains unexplained, partly due to our limited access to many of the models. Additionally, our approach aimed at creating a universally applicable test across different LLMs might have overlooked the nuanced performance differences in more complex reasoning tasks. We also focused on a subset of reasoning tasks, which may not fully represent the behavior of other task types. Lastly, we did not explore the effect of the distance between key paragraphs, leaving an aspect of LLM performance unexamined for future research.